The story of the Voyager probes begins in the present, not in the past, because even after nearly half a century traveling through the void, they are still alive. They still breathe. They still send faint and distant signals that cross billions of kilometers of darkness before touching antennas on planet Earth. In an age when almost everything is forgotten, these two small machines continue to challenge the very concept of finitude, drifting beyond the domain of the Sun into a region that scientists call interstellar space. Each radio pulse that arrives is a reminder that humanity still speaks to something that has already crossed all known frontiers. Today, Voyager 1 is the most distant human-made object in history. It is so far away that light, the fastest thing in the universe, takes more than 20 hours to make the journey between it and Earth. This means that any command sent takes almost a day to arrive, and the response, another day to return. It is a communication stretched across eternity, a slow dialogue between the present and a past that keeps moving forward toward infinity. The probe travels at more than 17 kilometers per second, enough to cross the diameter of Earth in less than 15 minutes. Yet even at this unthinkable speed, the universe still appears motionless and unfathomable before it. Voyager 2 follows closely behind, also beyond the Sun's direct influence. Both have crossed the invisible boundary known as the heliopause, the point where the solar wind, that constant stream of particles emitted by our star, loses its strength and blends into the interstellar wind, the breath of matter that fills the space between the stars. Crossing the heliopause is like leaving home and entering the cosmic ocean. No human being has ever been there. No other object we have built has traveled so far. And yet, both continue in motion, silent, persistent, carrying data, measuring magnetic fields, and sending reports from a frontier that until recently was only theory. These signals reach Earth with such faint power that they would be imperceptible to any ordinary antenna. They are captured by a network of giant parabolic dishes scattered across the world, known as the Deep Space Network. The radio waves that leave the Voyagers are fainter than the glow of a distant star, yet engineers manage to extract precious information from them: particle temperature, magnetic field intensity, variations in cosmic radiation. These are not data from telescopes, but from instruments that are actually out there, beyond the solar bubble, touching the unknown with ancient sensors that continue to resist cold, radiation, and time. Every new packet of data is a victory, because keeping these spacecraft operational is a daily struggle against the aging of systems built in the 1970s. The onboard computers are simpler than a modern calculator, and yet they continue to process instructions, adjust antennas, turn instruments on and off, and point their metallic bodies toward Earth to ensure that the radio beam finds the right path. It is like speaking to a mind that has been asleep for decades and still awakens when called. As you listen, Voyager 1 is crossing a region where the Sun no longer reigns. Out there, cosmic particles arrive from every direction, carried by the explosions of distant stars. The density of matter is so low that it would be impossible to find a single molecule in each cubic centimeter. It is almost absolute vacuum, absolute silence. And in that silence, the spacecraft keeps transmitting messages. The sound of the deep universe, converted into data and decoded by human antennas. The scientists who care for them say that every command is a gamble. The available energy decreases year by year because the nuclear generators, based on the decay of plutonium, produce less and less heat and therefore less electricity. It is like a heart that beats more slowly with every cycle, but still insists on living. And as long as there is enough energy to keep the transmitter alive, the Voyagers will keep answering, like old witnesses who refuse to fall silent. Thinking about this is remembering that we are listening to the echo of a human feat that began when computers were the size of entire rooms, when engineers still drew calculations by hand, and when no one imagined that one day there would be internet, mobile phones, or laptops, and yet the signal from those spacecraft still arrives, a thin thread of data, crossing billions of kilometers, cutting through the loneliness between the stars, and reaching the only planet in the known universe that managed to create something capable of going that far. What we hear today from the Voyagers is not just science, it is poetry in binary code. It is the sound of a mechanical miracle that still breathes in the dark. And as long as that signal exists, we will keep looking at the sky with the same question that guided the birth of these probes. How far can humanity go before silence swallows us? It is almost inconceivable to think that something built by human hands in the 1970s is still functioning in deep space, sending useful data, operating instruments, and obeying commands. 48 years is far too long for any machine. Metal expands and contracts, radiation corrodes circuits, temperatures drop to levels close to absolute zero, and the isolation of space itself makes every speck of cosmic dust a threat. Yet the Voyager probes remain active, sustained by a faint breath of energy coming from their nuclear hearts. Small generators that transform radioactive heat into electricity. These generators are known as radioisotope thermoelectric converters, and they work through the natural decay of plutonium. It is a slow, almost imperceptible process, but it releases enough heat to keep the spacecraft awake for decades. When they were launched in 1977, they produced about 470 watts of electrical power. Today, less than half of that still pulses through their aging cables. Each year, about 4 watts are lost, and the team of engineers on Earth must decide what to turn off so that the essential can remain alive. It is a patient and painful struggle. Every instrument that is shut down is a small funeral. First came the cameras, which had nothing left to photograph after leaving the planets behind. Then came the heaters of certain sensors, sacrificed to save power. Over time, other instruments were retired, until only the most resilient remained: particle detectors, magnetic field meters, and plasma systems. Even these are now counting down. With every shutdown, the spacecraft becomes a little quieter, but it still breathes. The Voyagers were built with redundancy. This means that in many systems there are duplicated components, 2 possible paths, 2 electrical routes. This characteristic has saved the mission many times over the years. When a circuit fails, engineers attempt to reconfigure the system, moving instructions to the healthy parts of the memory. It is a delicate process because the onboard computer is extremely limited. To put it into perspective, it has less memory than a simple modern digital watch, and yet it continues to process information, correct its trajectory, transmit data, and keep its main antenna pointed toward Earth. The persistence of these machines is, in truth, human persistence reflected in them. Every line of code sent, every orientation adjustment, every decision to turn off a heater to keep a transmitter alive, all of it is a proof of scientific love. The team that cares for the Voyagers is made up of engineers who often inherited the work of their predecessors. Generations succeed one another, passing the baton of cosmic vigilance. Many of those who launched the spacecraft are no longer alive, but the echo of their labor continues to travel through space. Imagine the technical challenge. The signal leaving Voyager's antennas has the power of an ordinary light bulb. By the time it reaches Earth, after crossing more than 20 billion kilometers, it is weaker than the background thermal noise, and yet it can be decoded, the data extracted, and the spacecraft's health reconstructed. The giant antennas of the deep space network, spread across strategic points on the planet, function as colossal ears, capturing the whisper of a lonely artifact lost in the interstellar night. But this is not only about technology, it is also about improvisation. Over the decades, the Voyagers have faced multiple crises. In one of them, the attitude control system began behaving erratically, threatening to make the spacecraft lose alignment with Earth. The problem was traced back to small thrusters that had been inactive for more than 20 years. With courage and ingenuity, the engineers decided to reactivate them, and to everyone's surprise, they worked. Thrusters that had slept for decades awoke, allowing the spacecraft to reorient itself. It was an almost emotional triumph. An ancient component revived to continue guiding humanity's gaze. The challenges did not end there. As the hardware aged, transmission systems and sensors began to fail. In some cases, engineers had to manually rewrite entire sections of code, transferring functions to areas of memory that were still intact. It is like operating on a patient thousands of kilometers away with tools from a bygone era. Every command is sent with extreme caution, because the delay in communication means any mistake could be irreversible. And yet, the spacecraft keep responding. They keep sending data that continues to astonish. They keep defying time, cold, vacuum, and mechanical death. And that makes us think, perhaps the reason the Voyagers are still alive is that, in some way, they represent something greater than science itself. They represent human determination. They represent the desire to endure. They are the symbol that even when everything seems distant, there is always a way to keep communicating. Today, every watt of energy is a philosophical decision. Turning off an instrument is like choosing what humanity will stop seeing first. And as long as there is enough electricity for an antenna to keep transmitting, there will be someone on the other side, listening, tuning frequencies, and decoding signals. The mission is no longer merely scientific. It is existential. It is proof that knowledge, when pushed to its limits, becomes faith in the persistence of life, even when that life is metallic, lonely, and cold. For more than 4 decades, Voyager 1 traveled in the dark, crossing storms of radiation and solar eruptions, surviving extreme cold and the erosion of time. But at a certain recent moment, the silence began to approach. It was the kind of silence that frightens even the most experienced engineers. One day, without warning, the probe began to send incoherent signals, unreadable data, lines of disconnected numbers, as if an ancient voice had started to whisper in a language no one understood anymore. It was the sign that something very serious had happened. For months, the scientists on the Voyager team lived between hope and despair. All they were receiving was noise, like a distorted echo coming from the edge of nothing. Voyager 1, the most distant human object in the universe, seemed to have lost its memory. It was as if a part of its brain had been eaten away by cosmic radiation. And the question hung in the air: what do we do when the most distant machine in the history of humanity simply forgets how to speak to us? The problem was in the flight data system, one of the most sensitive parts of the probe. It is responsible for organizing the information collected by the instruments and translating it into understandable packets before transmitting it back to Earth. Suddenly, that system began sending scrambled commands. The heart of the spacecraft was still beating, the radio signals were still arriving, but the words were broken. The engineers, trapped in time, had to deal with the colossal distance that turned every attempt at communication into a test of almost spiritual patience. Sending one instruction from Earth to Voyager 1 takes more than 20 hours. Waiting for the response takes another 20. Each attempt at diagnosis consumes almost 2 full days. Imagine the weight of that waiting. You send a message into deep space and only find out the next day if it was understood. At that slow rhythm, every mistake becomes an abyss. It was a cosmic chess match against the death of a machine that for decades has carried our voice toward infinity. When the team realized that the data system was compromised, the first hypothesis was that some chip had physically deteriorated. They went through old records, yellowed manuals, and diagrams drawn by hand by engineers who were no longer even alive. All of it in an effort to understand how the original software had been organized. And then came the idea that seemed impossible: move the damaged code to a different part of the memory, a region that was still functional. It was an extremely high-risk procedure. A single wrong line and the spacecraft could collapse completely. Even so, they tried. Using a carefully calculated sequence of commands, the engineers rewrote Voyager's fate almost 20 billion kilometers away. And then they waited. 20 long hours for the signal to travel, and 20 more for the reply to return. When the first coherent data packets began to appear on Earth's antennas, silence took over the control room. Then, tears. Voyager 1 had begun to speak again, but the miracle did not end there. Months later, another challenge appeared. The main radio transmitter began to fail, threatening to cut off communication completely. Once again, the engineers turned to the memory of the archives, searching for forgotten alternatives. They discovered that there was a second transmitter, turned off since the early 1980s. It had not been used for more than 40 years. And in a desperate maneuver, they decided to try to bring it back. The result was historic. The old transmitter woke up as if it had never slept. A prehistoric technology, with primitive circuits and wires corroded by age, answered faithfully. Humanity had done the impossible once again: repair a spacecraft in the interstellar abyss without ever touching it. And that feat, beyond being an achievement of engineering, was also a triumph of human persistence, the demonstration that care and curiosity can cross not only time, but also space. For the people who work on Voyager operations, every problem is personal. Every strange noise is a wound. These probes are not just scientific instruments, They are living witnesses of the era when we first began exploring the cosmos. Losing one of them would be like erasing part of humanity's memory. That is why when Voyager 1 started responding again, the entire planet seemed to exhale, because for a few months it had become a ghost, and ghosts do not usually come back. Today, the probe is still holding on, sailing through interstellar space with aging systems and fragments of code relocated. Its backup transmitter is still operating. Its instruments are still catching particles that come from the depths of the galaxy, and its nuclear heart is still pulsing, even if weaker each time. And behind every byte transmitted, there is a team of scientists who continue to speak to it as if it were an elderly friend, delicate and stubborn, who insists on staying awake when everyone else thinks it is time to sleep. The truth is that Voyager 1 is not just a spacecraft. It is a living metaphor for resistance, for continuing even when the body fails, when memory flickers, when the distance is too great for any return. It is proof that technology can have a soul, or at least something that looks like it, because in the end, it is not only the probe that survived, it is us, as a species, who remained present through it. Before becoming the most distant messengers of humanity, the Voyagers were born from a flash of genius, and from a cosmic coincidence that happens only once every century and a half. It all began when a group of astronomers and engineers, still in the 1960s, noticed something extraordinary. The 4 giant planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, would soon align in such ideal positions that a spacecraft could use the gravitational pull of one to reach the next. This rare alignment would open a unique window, a cosmic shortcut, making it possible to travel from world to world with minimal fuel. This sequence of gravitational assists became known as the GUIT, Grand Tour of the Planets, a concept so bold that it seemed like science fiction, even by the standards of that era. The idea was simple in theory, but monumental in practice: to launch a probe capable of using a planet's gravity to accelerate toward the next. In other words, to use the giants as cosmic slingshots. When a spacecraft enters a planet's sphere of influence, it is briefly captured by gravity, gains speed, and is then flung back into space, carrying a bit of that planet's orbital energy. It is a precise dance, calculated with formulas that must be tuned with the accuracy of a cosmic clock. And the greatest challenge, this alignment would only occur once every 175 years. If humanity missed the opportunity, it would have to wait until the 22nd century to try again. In the offices of the United States Space Agency, that discovery fell like a spark into a barrel of powder. The engineers' enthusiasm mixed with the administrators' skepticism. Many thought it impossible. After all, the plan required building a spacecraft that could survive more than a decade, cross billions of kilometers, operate without maintenance, and rely on electronics that would need to function continuously for decades, something no one had ever achieved before. Even so, there was a deeper conviction. If it worked, it would be the greatest scientific adventure in modern history. The team at the Jet Propulsion Laboratory, the legendary JPL, began to design the impossible. At first, the project was known as the Mariner Jupiter-Saturn mission, an expansion of the earlier Mariner probes that had explored Venus and Mars. But as ambitions grew, it became clear that this would be something entirely new. It would be a machine of unprecedented endurance and autonomy. Thus were born the twin sisters, the Voyager probes, designed to confront the very limits of human engineering. The calculations were so complex that for years, engineers used giant computers that occupied entire rooms just to simulate the possible trajectory. Each tiny typing error, each fraction of a degree in the launch angle, could mean total mission failure. And there was no room for full-scale testing. Everything had to work on the first attempt. The rocket would have only one chance to place them on the correct trajectory. There were no rescue plans, no way to fix mistakes along the way. If something went wrong, it would be the end before the beginning. But the technical challenge was only part of the equation. There was also the human challenge, convincing the government and the public that it was worth investing millions of dollars in 2 small spacecraft that would travel into a region of space from which they would never return. The world was in the midst of the Cold War, and the space race still revolved around rockets, satellites, and astronauts. Talking about sending robotic emissaries to the edge of the solar system sounded, to many, like a dream. Yet, the project was approved. And a new generation of engineers began building the most robust spacecraft ever designed. Every detail was thought out with obsession. The main body would be a hexagonal structure covered with aluminum panels and insulating material. The high-gain antenna, more than 3 meters in diameter, would be the heart of communication, always pointed toward Earth, even when the probe was billions of kilometers away. The instruments would be protected by layers of titanium and steel to withstand the brutal radiation of Jupiter's belts, and the spacecraft's brain would consist of 3 redundant computers capable of taking over one another's functions in case of failure. But the boldest element was the power source. Instead of solar panels, which would become useless so far from the sun, the Voyagers would be powered by nuclear generators. 3 small plutonium reactors would provide continuous electricity for decades, converting radioactive heat into electrical current. It was a risky bet, but essential. Only in this way could the spacecraft survive in the darkness of the outer planets, where sunlight is too weak to light even a lamp. Preparations lasted for years. Every screw, every weld, every circuit was tested exhaustively. The scientists knew there would be no second chance. When the 2 spacecraft were finally ready, the feeling was that something historic was about to happen. It was not just a space mission, it was humanity's attempt to send a symbol of its curiosity and ingenuity to the edge of the possible. And then, in the year 1977, the moment arrived. The Voyagers would be launched just days apart, into the unknown. No human could predict what they would see. But among the engineers there was a silent certainty. If they survived, they would forever change the way we look at the universe. The Grand Tour was no longer just a dream. It was the first step of a journey that has not yet ended, a voyage that continues today, sailing through the fringes of the cosmos, where the light of the sun is only a distant memory. The creation of the Voyager probes was an act of faith in engineering. There were no precedents, no guarantees of success. It was like trying to build a ship to cross an ocean no one had ever seen, using tools that barely existed. And yet, they did it. In the heart of the Jet Propulsion Laboratory, a group of engineers and scientists spent years designing and testing every component, imagining everything that could go wrong, from the radiation storms of Jupiter to the absolute freezing of deep space. The goal was simple and absurd at the same time: to create a machine capable of surviving alone for decades, with no maintenance, no repair, no rest, traveling through billions of kilometers in the dark. The body of the Voyagers was conceived as a compact and functional fortress, a hexagonal structure of aluminum and titanium, protected by layers of thermal insulation, houses the brain and the control systems. Attached to it, a high-gain antenna more than 3 meters in diameter, responsible for sending and receiving radio signals from Earth. That antenna would be the only link to humanity, a narrow and precise window that would have to remain pointed at our planet for the entire journey, even while the spacecraft spun through gravitational fields and powerful magnetic forces. If that antenna drifted out of alignment, the signal would be lost forever. To make sure that never happened, the engineers created an attitude control system that uses small thrusters powered by hydrazine. These are tiny jets, almost imperceptible, that correct the spacecraft's rotation at programmed intervals, as if it were breathing in rhythm with the cosmos. These thrusters work together with gyroscopes and star sensors, which allow the spacecraft to orient itself even in total darkness. It is a mechanical ballet that must function with absolute precision, with no room for error, because distance would make any failure irreversible. The heart of the Voyagers, however, lies in their power generators. Since no solar spacecraft could operate so far from the sun, the solution was the use of what are called radioisotope thermoelectric generators, compact reactors that transform the heat of plutonium into electricity. Each generator houses a small quantity of the radioactive element, carefully isolated, capable of supplying continuous energy for decades. At launch, each probe produced around 470 watts, enough energy to light a dozen lamps. And even so, it was with that small nuclear flame that the Voyagers would survive the eternal cold. Inside the main body, 3 independent computers form the electronic brain of the spacecraft: the attitude and articulation control system, responsible for maintaining orientation; the flight data system, which organizes the information collected by the instruments; and the command system, which interprets and executes the instructions sent from Earth. Each of them has built-in redundancy, a backup set that can be activated in the event of a failure. This architecture was the secret to the Voyager's longevity, the ability to reorganize themselves in the face of error. Even with the technological limitations of the time, the engineers created an organism capable of adapting in an almost biological way to aging and wear. The scientific instruments were another monumental challenge. The Voyagers carry high-resolution cameras, spectrometers, particle detectors, magnetometers, and plasma sensors. Together, they form a complete laboratory designed to investigate atmospheres, magnetic fields, rings, and moons. The instrument Boom, a metallic mast more than 2 meters long, was built with microscopic precision because any vibration or misalignment could compromise the measurements. And because sunlight is extremely weak in the outer regions, the cameras would have to operate with long exposures and precise thermal control to prevent the lenses from freezing. But the true miracle is in communication. The Voyagers transmit in the microwave band, and the signals sent by their antennas lose strength every additional billion kilometers. By the time they reach Earth, they are so faint that their energy is lower than that of a snowflake falling on the ground. And yet, thanks to the giant antennas of the Deep Space Network, with dishes up to 70 meters in diameter, it is possible to hear those metallic voices from the void. The modulation and error correction system was designed so that even the weakest messages could be recovered, byte by byte, through cosmic noise. The engineers knew they were building something that would never be repaired. Everything had to be perfect from the very first second. The Voyagers would be launched only once, and any failure would be eternal. That is why every weld, every screw, every circuit was tested under vibration, vacuum, extreme heat, and extreme cold. The goal was to simulate the conditions of space as faithfully as possible and to guarantee that the spacecraft would survive both the violent forces of launch and the absolute silence that would follow. And there was still one last challenge: time. The planetary alignment window was approaching. If the probes were not launched before the year 1978, the opportunity for the grand tour would be lost. It became a race against the clock and against physics. The Jet Propulsion Laboratory worked at a frantic pace. Engineers slept in the workshops, calculated trajectories by hand, corrected mistakes on paper and magnetic tape, and rewrote code on computers that today would look like toys. The atmosphere was one of euphoria and desperation, the kind of energy that drives decisive moments in history. When the two Voyagers were finally ready, the technicians knew they were standing in front of something greater than themselves. Those spacecraft were at the same time machines and symbols. They represented what is rarest in human beings: the courage to send a part of ourselves into the unknown with no expectation of return. And when they fixed the last panel in place and tested the final circuit, the engineers understood that they were creating more than robots. They were creating the seeds of the future. It was the beginning of a journey that would go beyond any calculation. Because when Voyager left Earth, it carried more than sensors and cameras. It carried the hope that human curiosity is, in itself, a form of eternity. The year was 1977. The planet was living through the height of the Cold War, and while world leaders measured their strength in speeches and arsenals, a group of silent engineers was preparing an achievement that had nothing to do with war and everything to do with infinity. In the deserts of Florida, at the launch complex of the United States Space Agency, two spacecraft rested in silence atop their Titan Centaur rockets, ready to leave planet Earth. They were Voyager 1 and Voyager 2, twin machines born from a rare combination of dream and precision. And although the world was distracted by political disputes and economic crises, something extraordinary was about to happen. Humanity was about to launch its first pair of eternal messengers into the unknown. The first to depart was Voyager 2, on the 20th of August 1977. Despite its number, it was launched before its more famous sister. The flight plan was strategic. Its trajectory would take it on a longer path, visiting Jupiter, Saturn, Uranus, and Neptune, a true cosmic tour among the giants of the solar system. Less than 3 weeks later, on the 5th of September, it was Voyager, Bahan's turn to lift off. Its route was more direct, faster, planned to reach Jupiter and Saturn before its twin, and then follow a course that would catapult it out of the solar system. The launch of each was a spectacle of precision and tension. The platforms trembled, the fuel tanks shuddered, and the engines roared with the power of thousands of tons of thrust. The sound spread through the air like metallic thunder, echoing between the control buildings. In the rooms of the Jet Propulsion Laboratory, engineers watched the flickering green screens, following numbers that rose and fell, each one representing the difference between success and tragedy. And when the final stage of the rocket detached and the Voyagers continued on their way, the relief was immediate. They were free. Earth had just launched 2 small artificial bodies into the abyss. During the first days, the team monitored every electronic heartbeat, every telemetry signal, adjusting parameters and confirming that the instruments were functioning properly. It was the beginning of a long journey, but at that moment, what mattered most was that both spacecraft were alive and healthy. The antennas unfolded, the instrument arms extended, and the sensors began to capture the first readings from interplanetary space. No one imagined that those readings would continue for nearly half a century. The Voyagers began their passage through the inner solar system toward the giant realms of Jupiter and Saturn. Week by week, their instruments measured variations in solar particles, dust, and magnetic fields. Everything was new. Until then, no spacecraft had gone so far. No engineer had ever followed a signal traveling such vast distances. It was the beginning of a story that would forever change the way we see space. On board, each Voyager carried not only scientific instruments, but also a symbolic message, a golden record, carefully engraved, containing sounds and images of Earth, music, voices, greetings in various languages, heartbeats, sounds of rain, ocean waves, and wind blowing through trees. It was the Voyager Golden Record, created by a team led by Carl Sagan, with the intention of sending into the cosmos a sample of what we are. None of the engineers knew if anyone would ever find it, but the message was clear. Humanity did not only want to explore, it wanted to be remembered. The following months were filled with adjustments and silence. The spacecraft traveled through interplanetary space like seeds carried by the wind. Each followed its own rhythm, with distinct trajectories but complementary objectives. Voyager 2, slower, traced the complete path of the Grand Tour, while Voyager 1, faster, prepared for the first encounters with the giants of the solar system. And as they moved away from Earth, the communication delay grew. Messages took minutes, then hours, and every command had to be planned with near military precision. As the Voyagers gained distance, the world continued its course. Wars, borders, governments, and ideologies changed, but out there in the silence, 2 small spacecraft moved steadily onward, representing all of humanity, without flags, without distinctions, without sides. They were literally messengers of a species still learning to coexist with itself, yet already daring to cross the void in search of meaning among the stars. With every million kilometers traveled, something within the team itself changed. The scientists began to realize they were not just observing the cosmos, they were becoming part of it. When the Voyagers passed beyond Mars's orbit and crossed the asteroid belt unharmed, the feeling was one of conquest and humility. For the first time, humanity had overcome one of the great barriers of space and was ready to look directly at the gas giants ruling the depths of the solar system. The engineers began to call the probes daughters of the sun, not only because they were born from its heat, but because they carried within them the spark of human curiosity, a light that would remain burning even when the sun became just a distant point. The launch of 1977 marked the beginning of a journey no one expected to last so long. And yet those 2 small spacecraft, made of metal, circuits, and willpower, proved that curiosity is a force stronger than any rocket. As the Voyagers drifted farther away, their signals grew weaker, but more precious. What left Earth that year was not just a scientific mission, it was a fragment of humanity itself. And as the Voyagers left our planet behind, they carried with them something no laboratory could ever measure, the desire not to disappear. After almost 2 years of travel, the silence of space began to change. The instruments on the Voyagers started registering an increase in radiation intensity, and the magnetic field detectors picked up powerful fluctuations. It was the sign that they were approaching Jupiter, the largest planet in the solar system, a colossal world of gas and storm so vast that more than 1,000 Earths could fit inside it. No spacecraft had ever come so close before, with cameras capable of seeing details. It was the first great encounter of the Voyagers, and it would also be the moment when humanity discovered an entirely new universe within its own solar system. As the spacecraft approached, the first images began to arrive. At first, they were just colorful spots, bands, and swirls. Then, as the resolution increased, hypnotic forms and movements began to emerge. Jupiter's clouds, made of ammonia and hydrogen, swirled in turbulent patterns, as if the planet were an ocean in perpetual frenzy. The Great Red Spot, that colossal storm that had lasted for centuries, was observed in detail for the first time. The Voyagers revealed it to be a gigantic cyclone, with winds of hundreds of kilometers per hour and a size large enough to engulf 3 Earth-sized planets. But the true shock came when the probes began to observe the moons. Before the Voyagers, it was believed that Jupiter's moons were cold and inert bodies, chunks of rock and ice frozen in time. Then came Hratsamagyo, and with it, the discovery that forever changed science's view of the solar system's worlds. In a sequence of images sent by Voyager 1, scientists noticed a strange moving spot on the moon's surface. Upon analyzing the frames, they realized something impossible, a column of material being expelled into space. It was an active volcano. Io was not only volcanic, it was the most volcanic body in the solar system. The Voyagers captured colossal eruptions, launching sulfur and lava hundreds of kilometers high. The heat came from Jupiter's gravitational force, which, along with the other moons, stretched and compressed Io's interior like a rubber ball, generating heat and energy. It was a form of volcanism never before imagined, driven not by internal magma, but by town gravitational stress. This discovery revolutionized our understanding of how energy can flow in distant worlds and opened the possibility that other bodies in the solar system, even far from the sun, could maintain geological activity or even enough heat to sustain complex internal environments. While Io burned with fire and sulfur, other moons danced in absolute contrast. Europa, for example, revealed an almost craterless surface, covered by smooth, cracked ice, like an ocean frozen beneath a layer of glass. The images suggested that beneath that crust might exist liquid water, a global ocean kept warm by the same gravitational stress that ignited Io. It was a silent but profound revelation. Perhaps, somewhere beneath that ice, life could exist. Voyager 1, and shortly after, Voyager 2 also flew over Ganymede and Callisto, immense moons with landscapes marked by craters and dark ice. Ganymede revealed itself to be the largest satellite in the solar system, even larger than the planet Mercury, and showed signs of having its own magnetic field. Callisto, on the other hand, displayed a violent past, covered in scars from impacts that told the ancient story of the solar system's birth. Each image that arrived was a window opened into the unknown, but Jupiter was more than its moons. The Voyagers recorded the power of its radiation belts, magnetic fields so intense they could destroy ordinary electronics instantly. The planet was a living storm, an electric titan spinning at absurd speed. A Jovian day lasts less than 10 hours. At the edges of its atmosphere, lightning danced on planetary scales, and its magnetic field, hundreds of times stronger than Earth's, created auroras that would make any sunset seem insignificant. The passage through Jupiter was a baptism for the Voyagers. They survived radiation, magnetic pressures, and storms. Their instruments endured, their systems responded, and their electronic eyes showed humanity a spectacle no one had ever seen. For the first time, the solar system ceased to be a collection of distant points and revealed itself as a vibrant stage full of living, dynamic, and mysterious worlds. The scientists could barely keep up with the flood of information. Tens of thousands of images and readings were analyzed for months, and the more they discovered, the more questions arose. Io and Europa, above all, changed the understanding of habitability in the cosmos. If one of Jupiter's moons could have heat, water, and energy, then the universe could be filled with similar places, hidden beneath layers of ice and silence. As the Voyagers moved away from Jupiter, they carried more than scientific data. They carried an emotional message. Humanity had just seen with its own eyes that the cosmos was far more active and diverse than it had ever imagined. There was fire, ice, oceans, and storms on scales that defied comprehension, and if Jupiter was the first act of this cosmic symphony, the next would be even more breathtaking. Because just ahead was Saturn, the Lord of the Rings, the planet that would turn the universe's beauty into form. After the encounter with Jupiter, the Voyagers continued their journey toward their next destination, Saturn, the planet that had fascinated humanity since antiquity with its mysterious appearance and shimmering rings. Seen from Earth, it had always been a jewel suspended in the dark, a golden sphere encircled by an almost ethereal disk. But no one, not even the most experienced astronomers, imagined what truly lay hidden there. It would take until the end of the 1970s for two small spacecraft, traveling alone through the void, to reveal the truth. Saturn's rings were not a simple adornment, but a dynamic, complex, and ever-changing system, a symphony of ice and gravity. Voyager arrived first in November of 1980. As it approached, its cameras began to capture a spectacle never before seen. The rings, which from Earth seemed smooth and continuous, were revealed to be made up of countless particles of ice, rock, and dust, orbiting in perfect harmony. There were thick rings, thin ones, translucent bands, and even regions with gaps and wavy edges. It was as if the planet were wrapped in a disk of crystals, held together by gravity. The images transmitted by the probe revealed surprising structures, small moons hidden among the rings, responsible for sculpting paths and gaps with their gravitational pull. These tiny companions, called shepherd moons, act like cosmic gardeners, guiding the motion of particles and maintaining order within chaos. With every orbit, they create ripples, arcs, and sharp boundaries, turning the ring system into something alive, pulsating, and constantly evolving. It was the first time humanity understood that the rings were not a single solid body, but an ocean of fragments orbiting in synchrony, obeying an invisible choreography. But Saturn's spectacle was not limited to its rings. Its moons, observed up close for the first time, revealed entire worlds, each with its own landscapes and mysteries. The moon Titan, in particular, captured scientists' attention. Larger than the planet Mercury, it was shown to have a thick yellowish atmosphere rich in methane and nitrogen. It was a unique case in the solar system, a moon with weather, with clouds, and with winds blowing in opposite directions in different atmospheric layers. The Voyager's cameras could not see Titan's surface, shrouded by dense haze, but their instruments confirmed the presence of organic molecules, the same ingredients that, billions of years earlier, had given rise to life on Earth. For many scientists, it marked the beginning of a new question. Could Titan hide oceans beneath its cloud layers? That doubt would only be answered decades later with other missions. But the Voyagers were the first to suggest that worlds seemingly cold and distant might have chemical conditions similar to those of our primordial planet. Meanwhile, Saturn's atmosphere revealed both beauty and violence. The images showed vast storms, colorful bands in tones of gold and brown, and swirling patterns stretching thousands of kilometers. Like Jupiter, Saturn is a gas giant composed mainly of hydrogen and helium, but its atmospheric behavior is more subtle, more graceful. As if the planet breathed in a slower rhythm, the Voyagers even captured the glow of lightning flashing beneath the clouds, bursts of energy illuminating the tops of storms like signs of electric life. And then came the most famous view, the planet backlit with the sun behind it. From that angle, the rings glowed like cosmic dust suspended in liquid gold. It was the first time humanity had ever seen Saturn illuminated in that way, and the image became one of the most iconic in the history of space exploration. Scientists and lay people alike were mesmerized. It was a reminder of how small Earth seemed before such grandeur, and of how the universe could be both simple and incomprehensibly beautiful. Shortly after, in August of 1981, it was Voyager 2's turn to repeat the feat, passing by Saturn and confirming its sister's discoveries. It observed the moons in greater detail, and sent back new images of the rings, revealing even finer structures formed by subtle gravitational interactions. Scientists began to realize that Saturn's system was a microcosm within the solar system itself, a natural laboratory for studying planetary formation and orbital dynamics. But the encounter with Saturn would also mark the separation point between the two probes. After this stage, their trajectories would diverge. Voyager 1, propelled by Saturn's gravity, would be flung out of the plane of the solar system, heading toward the interstellar void. Voyager 2, on the other hand, would use Saturn's gravitational assist to continue on toward Uranus and Neptune, becoming the only spacecraft in history to visit all 4 gas giants. Saturn was, therefore, more than a destination. It was a gateway. It marked the end of the primary mission and the beginning of the unknown. From that point on, the Voyagers would cease to be mere explorers of planets and would become witnesses of the cosmic vastness. And while the engineers on Earth celebrated their success, few realized that the best was yet to come, because what Voyager 2 would see at Uranus and Neptune would once again redefine what we understand as a frontier. Uranus had always been a planet wrapped in mystery. Even when seen through the best telescopes, it looked like nothing more than a distant, silent blue-green sphere. No human being had ever visited it, and no other spacecraft besides Voyager 2 has ever flown past it. It was in January of 1986 that this solitary probe approached the 7th planet from the Sun, and in a matter of hours, completely rewrote what we knew about that frozen world. Uranus is a planet unlike any other. It spins on its side, literally tilted at an angle of almost 90 degrees. While Earth spins like an upright top, Uranus rolls like a ball, exposing its poles directly to the Sun for long stretches. Each hemisphere faces 42 years of continuous daylight, followed by 42 years of total darkness. Before the Voyagers, no one understood the cause of this strange tilt. Today we know that it was likely struck billions of years ago by a colossal body, perhaps the size of Earth, an impact that altered its axis and shaped its rotation forever. As Voyager 2 approached, the planet looked calm, almost lifeless in terms of atmosphere. Unlike Jupiter and Saturn, there were no turbulent bands, no obvious storms. Its atmosphere looked like a uniform haze of frozen methane. But the probe's instruments revealed what the eyes could not see: winds slicing across the tops of the clouds at hundreds of kilometers per hour, and subtle temperature variations that indicated internal flows of heat. Beneath that serene blue, Uranus was a silent furnace of energy. The instruments also detected something unexpected. Uranus's magnetic field was chaotic. It was not aligned with the axis of rotation, nor even centered within the planet. It was displaced and tilted, a magnetic labyrinth spinning in an irregular way, which made the environment around Uranus extremely complex. This discovery intrigued scientists and helped establish that the icy giants have magnetic behaviors that are very different from those of the gas giants. But the spectacle did not end with the planet itself. Voyager 2's cameras revealed a set of thin, dark rings orbiting around it, almost invisible. They were not bright like Saturn's, but formed a subtle, fragile system made of particles of ice and dust, coated with dark material, possibly carbon. The existence of these rings had been suggested shortly before the mission, but it was Voyager that confirmed and mapped each of them, showing that Uranus, distant as it was, also possessed its own crown. And then came the moons. 13 were known before the flyby, but Voyager 2 discovered 10 new ones, revealing a true miniature planetary system. Among them, Miranda astonished scientists the most. Its images showed a shattered and rebuilt world with gigantic faults, cliffs 20 kilometers high, and plains blended with deformed craters. It looked like a collage of fragments, as if Miranda had been destroyed in an impact and then reassembled by gravity. Each image transmitted felt like a memory of violence and rebirth. Other moons also stood out. Ariel and Umbriel showed signs of ancient geological activity, with deep canyons and relatively young surfaces, suggesting that they may once have had internal heat. Titania and Oberon, the largest, revealed landscapes of ice and rock marked by fractures and enormous craters. Each one told a different story about the balance between cold and energy, about how worlds that appear frozen and dead today may once have been dynamic. The flyby lasted only a few hours, but it left behind a legacy that still fuels imagination to this day. Voyager 2 passed just over 80,000 kilometers from the tops of the clouds and, in a matter of instants, captured the entirety of a planet that no one would ever again see up close. Since then, Uranus has remained untouched, watched only from afar by telescopes. Everything we know about its weather, its rings, and its moons comes from that brief visit. As it left the planet behind, the probe sent one last sequence of images, the bluish glow of Uranus outlined by the distant sun. It was a farewell, cold and silent. Voyager 2 had completed yet another chapter of its mission, and now it was heading toward an even more remote destination, Neptune, the last giant planet, the visible edge of the solar system. When Voyager 2 left behind the pale glow of Uranus, there was a quiet sense of closure among the control team. No one knew for sure if the spacecraft would survive another planetary encounter. Its systems were aging, its thrusters weary, and the distance from Earth was now so immense that any command took nearly 5 hours to arrive. Even so, in August of 1989, 12 years after its launch, the probe achieved a feat no other human-made object has ever repeated. It reached Neptune, the last giant planet of the solar system. It was humanity's final farewell to the known worlds, the last stop before infinity. Neptune is a planet of extremes. Located more than 4 billion kilometers from the Sun, it receives less than 1,000th of the sunlight that reaches Earth. And yet, it is one of the most active worlds in the solar system. Voyager 2 discovered that despite its distance and intense cold, Neptune is a living, dynamic planet, filled with winds, clouds, and colossal storms. Its images revealed bluish bands and dark spots, showing an atmosphere in constant motion. The most famous of them, the Great Dark Spot, was a storm as vast as the entire Earth, rotating at nearly 2,000 kilometers per hour, the fastest winds ever recorded on any planet. The beauty of Neptune's images astonished even the most experienced scientists. The deep blue of its atmosphere, caused by methane absorbing red light, gave it a hypnotic, almost liquid appearance. It was like staring into the frozen abyss of the universe itself. White clouds of methane and ammonia moved in layers, casting shadows on darker storms below. The contrast between light and shadow gave the impression of a living ocean stirred by invisible forces. And then came an even more intriguing discovery. Neptune's magnetic field was also misaligned, like Uranus's, but rotated at a different tilt and with surprising strength. Measurements showed that the planet emitted radiation in complex patterns, probably generated by deep electrical currents within its interior. It was yet another clue that the icy giants held secrets that physics still did not fully understand. But perhaps the most striking moment of the encounter was the meeting with Triton, Neptune's largest moon. The images revealed something absolutely unexpected. Geysers of frozen nitrogen erupting from the surface into space. It was the first time geological activity had ever been observed on a world so far from the Sun. Triton's ice was not dead. It breathed. Voyager 2 recorded jets rising 8 kilometers high, leaving dark trails across the pale pink terrain. This meant that Triton had an internal heat source, likely generated by Neptune's tidal forces, the same kind of energy that kept Io Volcanic and Europa warm. Triton also revealed another peculiarity. It orbits Neptune in the opposite direction of the planet's rotation. This indicates that it was probably a captured body, perhaps a former dwarf planet, wandering through the solar system until it was trapped by Neptune's gravity. This retrograde orbit seals its tragic fate. One day, in a distant future, it will be torn apart by tidal forces, feeding new rings around the planet. Voyager was the only close witness to this doomed moon. During closest approach, the probe passed just 5,000 kilometers above Neptune's cloud tops, an act of astronomical precision. It then performed a final maneuver, flying by Triton and using its gravity to slingshot itself onto a trajectory that would forever escape the pull of the planets. It was the last dance of a mission that had crossed the entire solar system. When the sequence of images ended and the signal began to fade, the control center on Earth fell into an almost reverent silence. It was the end of the grand tour. With Neptune and Triton, Voyager 2 closed the era of the great planetary explorations of the 20th century. No spacecraft has ever traveled that far again. What began as a 4-year project became a journey of decades, and with every new world, the Voyagers expanded the frontier of human knowledge. The passage by Neptune was, in a way, a farewell, the last human look at the Sun's worlds before plunging into the interstellar ocean. As the spacecraft slowly drifted away, its instruments still recorded echoes of the solar wind, and its cameras, before being shut down, captured the final images of a planet shining like a cold jewel in the dark. And then, like a traveler turning off the lights before leaving, Voyager 2 powered down its cameras, pointed its antenna toward Earth, and let silence take over the space around it. The solar system had been mapped. All its giants had been visited, and for the first time in history, humanity had extended its presence to the edge of its cosmic home. The next step would be something no one had planned: to cross the final frontier, the region where the sun's domain ends and interstellar space begins. At the heart of the Voyager journey lies a secret of mathematical elegance and physical beauty that turned the impossible into reality. This technique, known as gravitational assist, was the true fuel that allowed the probes to cross the giant worlds and escape the solar system without needing more propulsion. Without it, the Voyagers would never have reached Saturn, Uranus, Neptune, or interstellar space. It was a precise choreography of mass, velocity, and gravity, a dance between human machines and the very gods of the cosmos. The idea seems magical, but it is pure physics. When a spacecraft approaches a moving planet, it temporarily enters the planet's sphere of gravity. In that moment, it is pulled toward the planet, accelerating. And as it leaves this region, if its trajectory is calculated at just the right angle, the spacecraft is flung outward, carrying with it a fraction of the planet's orbital momentum. It is as if the planet lends part of its motion energy to the craft, which then flies away faster, like a stone launched by a cosmic slingshot. The most remarkable thing is that this acceleration requires no fuel at all. It is a free push given by nature itself. The engineers of the Voyager missions discovered how to turn gravity, a force usually associated with falling, into thrust. They used the pull of the planets not to slow down, but to accelerate. This maneuver, calculated with almost absurd precision, allowed each planetary encounter to serve as a springboard for the next. Jupiter launched the probe to Saturn. Saturn propelled it toward Uranus, and Uranus flung it toward Neptune. Each step was a curve through space carefully rehearsed, and each planet a natural catapult. The beauty of this technique lies in its dependence on the universe's own rhythm. The rare alignment of the planets, which occurs only once every 175 years, was the perfect stage for executing this plan. The Voyager's entire trajectory was designed to take advantage of this cosmic coincidence, and each maneuver demanded calculations that bordered on the impossible. Even the tiniest error in timing, a deviation of just seconds, could have sent the probes into the void away from the planets. And yet, everything worked. Every passage was a stroke of perfection. This sequence of gravitational assists accelerated the probes to unimaginable speeds. Voyager 1, for example, left the solar system traveling at more than 17 kilometers per second, enough to cross the distance between Earth and the Moon in just 6 hours. And even at that unthinkable speed, the universe ahead still seems motionless, like an endless ocean. That is the paradox of the cosmos. The faster you go, the farther infinity recedes. But the lesson the Voyagers left us is not only scientific, it is philosophical. They showed that progress at its core is the art of using the very forces that once seemed to oppose us. Gravity, once seen as a prison, became freedom. What pulls us down was used to lift us higher. It is the perfect metaphor for the human spirit itself, turning limits into momentum, turning the weight of reality into movement toward the unknown. During the maneuvers, the spacecraft performed turns so precise that each one was the equivalent on scale of threading the eye of a needle millions of kilometers away. The probe had to pass through the exact point behind the planet to draw the maximum energy. Any error and it could collide, veer off course, or even be captured and destroyed by the planet's gravity. But there were no errors. The trajectories were flawless. Every signal sent, every minuscule correction fired by the thrusters was part of a ballet calculated with the serenity and precision of those who understand the language of the universe. The result was so perfect that, decades later, the Voyager's flight paths are still studied as masterpieces of cosmic navigation. They became the model for all missions that followed: Galileo, Cassini, New Horizons, and many others that used the same principle to reach distant worlds. It is as if the Voyagers had written a new grammar for space exploration, teaching humanity that gravity, the power that keeps us anchored to Earth, can also be the path to freedom. And while the two probes continue to drift, carrying the borrowed energy of giants now far behind them, the metaphor endures. Every leap toward the unknown begins with an impulse from where we stand. The Voyagers did not flee the solar system. They were propelled by it. That is why, in a sense, even at the edge of interstellar space, they remain connected to the sun. They carry the strength of the worlds that launched them, and through them the entire solar system continues to move, echoing through the void as an eternal symphony of gravity and light. When the Voyagers were launched, the official expectation was simple and modest. Survive for 5 years, long enough to reach Jupiter, fly past Saturn, and send back some images and measurements. That was it. 5 years. But reality surpassed any human dream. When that deadline ended, the two spacecraft were only beginning to show what they were truly capable of. Their systems were still working, their nuclear generators were still steady, and the instruments were transmitting data as clear as on the first day. The team realized that in front of them there was something far greater than a simple technical plan. What began as a primary mission was about to become an endless journey. Starting in 1981, when Voyager 2 completed its passage by Saturn, the original timeline was officially closed. The formal objectives had been met, but no one on the team wanted to turn the probes off. How do you shut down a dream that is still breathing? In internal meetings, the scientists decided to propose an extension. Take advantage of the spacecraft's good health and keep exploring. That's how the extended mission was born. A second phase that would take the Voyagers to places never before imagined. Uranus and Neptune. What no one imagined was that this extra phase would become the most important of all. It was during the extended mission that we discovered Io's volcanoes, Europa's oceans, Saturn's auroras, Neptune's winds, and Triton's geysers. Each of these discoveries redefined the human view of the solar system. And when Voyager 2 completed the grand tour, passing by all 4 gas giants, it became clear that the limit was no longer technical. It was philosophical. What comes after seeing everything? The answer emerged naturally. Continue. After Neptune, there were no more planets ahead, only the abyss. But the Voyagers were still alive, and something fascinating lay just beyond, the invisible frontier of the Sun, the region where the solar wind weakens until it blends with the interstellar wind. It was an area never explored, a theoretical territory known only through calculations. The scientists realized they could use the spacecraft as messengers beyond the Sun's direct influence. That's how the third phase was born, the Voyager interstellar mission. This new stage wasn't just an extension, it was a reinvention. The probes would have to operate for decades, enduring extreme cold and the inevitable aging of their systems. The engineers began saving energy, shutting down instruments, rerouting routines, and recalculating transmissions to conserve every watt. It was a work of patience and endurance. The same spirit that had guided the launch in 1977 now repeated itself, but in a quieter form. The fight against time. Meanwhile, humanity was changing. Personal computers were becoming common. The internet was being born. New space missions were launching, and satellites were orbiting planets that hadn't even been on the radar when the Voyagers left. And yet, out there, more than 10 billion kilometers away, 2 small spacecraft were still sending data back to Earth as if time had not passed. It was as if the 20th century was still breathing in space. In the following years, the Voyagers kept crossing the outer solar system, measuring particle flow, the magnetic field, and the density of the solar wind. Every bit of information was precious. The scientists began to realize they were approaching something unprecedented. The Heliopause span, the boundary where the Sun's domain ends. It was a distant dream, something no one expected to witness. The probes, which had been designed to live only 5 years, were about to become the first human messengers to cross the threshold between our system and interstellar space. But before they could get there, they had to survive the distance. The signals were becoming weaker and weaker, and cosmic noise was beginning to blur the transmissions. The communication delay had already surpassed 16 hours to go out and another 16 to come back. Every command was sent with the care of someone speaking to a voice living in the past. The control team, now partly made up of the sons and grandchildren of the original engineers, treated the probes like old friends, aged but stubborn. There was care, respect, and a sense of reverence. It was during this period that Voyager 1 did something that would turn its journey into one of humanity's most beautiful stories. Before saying goodbye to the planets, the team decided to perform one last maneuver. Turn the spacecraft's camera back toward Earth and take a picture. It was a risky idea because the sun could damage the sensors, but the resulting image would become one of the most iconic of all time. The photo of the pale blue dot, Earth reduced to less than a pixel, floating in a sunbeam, an almost invisible speck, lost in the dark. Carl Sagan, one of the visionaries behind the mission, described that image as a lesson in cosmic humility. In front of that single point, all human pride dissolved. There was everything that had ever existed. Every king, every war, every love, every tear, every belief, all of it in one tiny reflection. It was the entire planet seen from the edge of the solar system, and with that symbolic gesture, the primary mission came to an end. The cameras were shut down, but the spirit of exploration remained lit. From that moment on, the Voyagers stopped being just scientific machines and became existential symbols. They were no longer traveling only to collect data. They were traveling to remind us of what we are, explorers by nature, incapable of staying still. The end of the primary mission was, in truth, the beginning of a new kind of journey, humanity's spiritual crossing outward from its own cosmic home. And so, even after 40 years, both spacecraft are still moving forward. Their antennas are still pointed toward Earth, and their nuclear hearts still provide enough heat to keep the transmitters alive. They are not only traveling through space, they are traveling through time, carrying with them the story of a planet that once wanted to touch the stars. For billions of years, the sun has reigned supreme over its cosmic bubble, an invisible sphere of wind and energy that surrounds all the planets, asteroids, and comets of the solar system. This bubble, called the heliosphere, is humanity's natural shield. Within it, everything is bathed in the particles released by the star, protons, electrons, and magnetic fields, traveling millions of kilometers per hour, repelling interstellar radiation and shaping the boundaries of the sun's domain. For centuries, no one knew exactly where this influence ended. Was it a sharp border like a wall, or a gradual fade, like a sunset dissolving into the horizon? The answer began to arrive when the exhausted Voyagers approached the final edge. Voyager 1 was the first. In August of 2012, after 35 years of travel, its instruments recorded a sudden and profound change. The particles of solar origin, those constantly flowing from the sun, almost completely vanished. In their place appeared particles of extremely high energy, coming from beyond. At the same time, the direction of the magnetic field shifted slightly, and the plasma density increased. These were unmistakable signs. The probe had crossed the heliopause, the boundary where the solar wind surrenders to the interstellar wind. For the first time, a human object was outside its home. The news spread across the world like a whisper of awe. Scientists, writers, students, and dreamers paused for a moment to imagine what it meant. A machine built on Earth, launched in the 1970s, had gone beyond the sun's influence. Voyager 1 was now in a region where no spacecraft, no human light, and no hope of return could reach. The silence out there is almost absolute, and yet it kept speaking to us. 7 years later, in November of 2019, Voyager 2 repeated the feat, crossing the heliopause in a completely different region of space. Comparing the two crossings revealed something extraordinary. The edge of the solar system is not a perfect sphere, but a deformed isometrical bubble. The interstellar wind pushes the heliosphere as the ocean pushes the bow of a ship, compressing it on one side and stretching it on the other. This showed that the solar system, far from being a static territory, is a vessel sailing through galactic currents. The moment the Voyagers crossed the sun's frontier was more than a technical milestone. It was a philosophical gesture. For the first time, something human was truly an outside of home. Every signal that now reaches Earth travels through a sea of particles and magnetic fields that no longer belong to the sun. It is a completely new environment, where space becomes denser and the plasma temperature rises in unexpected ways. These data are still being studied today, for no other human instrument has ever measured what lies beyond. But there is one detail that makes it even more poetic. Although the Voyagers are beyond the heliosphere, they still feel the sun. Its gravity still holds them, imperceptibly. This means that even in interstellar space, they still, in a way, belong to our system. It is as if the sun were extending its invisible arms, holding its most distant daughters by the fragile thread of gravity. Crossing the heliopause was not a moment of spectacle, but of serenity. There was no light, no sound, no visible event, only numbers slowly changing, graphs shifting, until scientists realized we had crossed a frontier that once existed only in theory. It is a perfect metaphor for science, the silent act of turning the unknown into reality. With that crossing, The Voyagers ceased to be planetary explorers and became interstellar ambassadors. They now measure the pulse of space between the stars, recording subtle variations in cosmic radiation, galactic magnetic fields, and high-energy particles. These data help us understand how the Sun interacts with the environment of the Milky Way, and how Earth, protected by this bubble, is spared from the constant bombardment of lethal particles from the cosmos. The invisible frontier of the Sun is therefore a mirror. On one side lies the familiar region that shelters us, on the other, the absolute unknown, and the Voyagers are the bridge between these two worlds, the symbol of a species that chose to step through the gate and keep walking, even without knowing what it would find. Today, when the faint signal from the probes reaches Earth, traveling billions of kilometers through the dark, it carries more than data. It carries the echo of the crossing, the sound of a small human artifact that dared to leave its stellar cradle and drift alone through the galactic vastness. On February 14, 1990, an improbable request was made by a man who saw more poetry in science than many poets see in their own words. Astronomer and science communicator Carl Sagan suggested to the Voyager mission team that before permanently shutting off Voyager 1's cameras, they should turn its lens back toward Earth. By then, the spacecraft was more than 6 billion kilometers away, on the verge of leaving the solar system. The Sun was no longer anything but an ordinary star, and the planets were nothing but specks drowned in glare. Still, Sagan insisted, turn it around, let it look home one last time. The engineers hesitated. The maneuver was dangerous. Sunlight could damage the camera sensors, and the risk of failure was high. But the idea was irresistible. Voyager had seen all the planets, from Jupiter to Neptune, and now, before moving on, it would have the chance to look back at where it all began. The spacecraft was programmed to take a sequence of 60 photographs, a panoramic mosaic that would become the family portrait of the solar system. Among that set, one image would be different, one image that would later forever change the way humanity sees itself. In that photograph, Earth appears as a mere dot, a pale pixel suspended in a sunbeam reflected across the camera's optics. A patterned pale blue dot is drifting in an immensity of infinite darkness. There are no borders, no continents, no hint of humanity, only a nearly invisible spark, so small you could hide it with the tip of your finger. And yet inside that tiny spark is everything we are and everything we have ever been. When the image was revealed, the impact was silent and devastating. Carl Sagan wrote about it with a sensitivity that passed through generations. He reminded us that in that blue point are all of our loves, all of our wars, all religions, ideologies, civilizations, and stories. Every king and peasant, every prophet and traitor, every child and killer, every tear and smile, all of them lived and died there, on that mote of dust suspended in a sunbeam. The passing pale blue dot became a mirror for humanity. It forces us to confront the true scale of our arrogance and the fragile beauty of our existence. Faced with that image, empires feel irrelevant, borders vanish, and even time itself seems to bow to the vastness of the cosmos. It is a necessary cruelty. Earth is only a tiny, vulnerable, solitary home lost in the cosmic ocean, but there is something deeply comforting in that smallness, because even while being almost nothing on a universal scale, we manage to look into infinity and understand it. We built instruments capable of showing us where we are and who we are, and that may be the most extraordinary achievement of all. In the middle of darkness, we made light. The Voyagers were the authors of that vision. The same cameras that captured Io's volcanoes, Saturn's rings, and Neptune's storms were the ones that, for a brief instant, showed us the reflection of our own fragility. The pale blue dot is the visual epitaph of the era of great planetary exploration, a farewell from a spacecraft that looked back and saw its creator as a tiny reflection, lost in time. After that image, Voyager's cameras were shut off forever. They had fulfilled their purpose. The spacecraft would continue in silence, now operating only with its scientific instruments, but that last look remained burned into humanity's memory. It was the first time we literally saw what we truly are, a spark. The solar system family portrait, assembled from the 60 images, revealed something deeper as well. When the photographs were aligned, they showed every known planet, each one a point, a color, a glimmer. None of them special, none of them grand. And at the center, the sun, just a star among billions. That collage of colored points was the true map of human humility. It was the universe reminding us that greatness isn't in the size of our world, but in our ability to look at it and grasp its worth. With the pale blue dot, the Voyagers transcended science. They stopped being only machines and became symbols of awareness. They showed that even though we are small, we are the only known form of life capable of understanding its own place in the cosmos. And that changes everything. Because from that moment on, there is no longer out there and in here. There is only the universe, and us, tiny and astonished, trying to understand it. While the Voyagers were being prepared for their journey, the scientists realized that something much larger was at stake than just exploring planets and measuring magnetic fields. This would be the first time a human-made object truly left the solar system. It was inevitable that one question would emerge. If one day in a distant future, some other civilization found these probes, what would it learn about us? What had we left behind of humanity if the rest disappeared? It was from this restlessness that one of the most beautiful and poetic gestures in scientific history was born, the Voyager Golden Record, a symbolic portrait of who we are, engraved to survive billions of years. The idea came from a team led by Carl Sagan, who believed the mission should not only be technical, but also philosophical. For him, sending a probe into interstellar space was simultaneously a scientific act and an act of communication. And if, at some point in the future, an intelligent life form found one of the Voyagers, it should know that, on a small blue planet, lived a conscious species capable of love, creativity, and dreaming. So Sagan and his team conceived a cosmic time capsule, a disk made to traverse infinity. The Golden Record was constructed of gold-plated copper, designed to withstand radiation and the wear of time. Each was affixed to the side of the probes, protected by an aluminum cover that contained instructions encoded in symbolic language for how to reproduce its contents. Among these instructions were diagrams explaining how to locate Earth relative to specific pulsars, as well as a drawing showing how to decode the recordings and interpret the sounds and images. It is a universal manual, written for minds that may never have seen a human. The disk's content is a moving blend of science, art, and emotion. On it are recorded sounds of Earth, the roar of the ocean, the song of birds, the sound of wind, thunder, a kiss, and even the heartbeat of a woman, the human heart echoing through the cosmos. There are also greetings in 55 languages, from Sanskrit and Hebrew to Japanese and Portuguese, Brazilian variety, with a simple message: peace and happiness to all. But the disc also contains music, a selection of 27 tracks chosen to represent the planet's sound diversity, from Louis Armstrong's jazz to traditional African melodies, from Bach and Beethoven to a native Peruvian song, from Gregorian chant to Chuck Berry's early rock Johnny B. Good. Including popular music was a bold choice, a way of saying that human art does not belong only to the erudite, but to the spontaneous. And in the middle of it all is the most universal sound of all, a child's laughter. In addition to the sounds, the disc carries 116 images, converted into analog data pulses. They show Earth's and humanity's diversity: landscapes, mountains, forests, rivers, human faces, cultures, architecture, anatomy, animals, and even scientific and mathematical diagrams. There is also DNA structure, the solar system, and basic chemical elements of life. No text explains the meaning. Everything is left to interpretation by whoever someday might decode the code. But there is something even more symbolic, a recording with the voice of Kamwan Druyan, collaborator of the project and Carl Sagan's wife. It is not just a speech, it is a record of her own brain waves, captured while she thought about love, humanity, and eternity. In a poetic sense, the Voyager carries not only the images and sounds of Earth, but the mind of a human being, our species' mind literally inscribed in gold, traveling among the stars. Sagan described the Golden Record as a bottle cast into the cosmic ocean. The chance of its discovery is almost nil, but the gesture matters. Sending that message was an act of faith, the demonstration that, despite being aware of the universe's immensity and loneliness, we chose to cry out to the void, saying we exist. It was humanity's way of asserting its presence, not with arrogance, but with tenderness. Today, each Voyager carries one copy of the disk in opposite directions. Even after their batteries are exhausted and their transmissions cease, the disks will survive intact for billions of years, drifting among the stars. Perhaps, in an unimaginable future, a distant civilization will find them. Perhaps they will never be found, but that doesn't matter, because the real recipient was always ourselves. The Golden Record reminds us that, even amid chaos and destruction, we are a species that tries to communicate beauty, that wishes to be understood, that facing eternal silence still believes it is worth sending a hello. And as the Voyagers continue their path, those disks continue with them, carrying the heart of planet Earth, a golden message floating in infinite darkness. Every second of the Voyagers' lives today is a victory against time. They were built to last 5 years, and they have already surpassed 4 decades of operation. Now, drifting through interstellar space, they are at the absolute limit of their strength. What once was a scientific mission has become a silent race for survival. The fuel for their chemical thrusters is nearly gone, their instruments are aging, and the heart of each spacecraft, its nuclear generator, beats ever more weakly. The question that echoes among engineers and scientists is simple and inevitable: how long will they last? The Voyager's energy comes from their radioisotope thermoelectric generators, devices that convert the heat of plutonium into electricity. On launch day, each probe produced about 470 watts of electric power. Today, after nearly 50 years of radioactive decay, barely more than half of that remains. Each year, around 4 watts fade away, like a candle burning slowly in the dark. This constant loss forces the team to make painful decisions: what to turn off so that the essentials may stay alive. Over the past decade, one instrument after another has been shut down. First came the heaters for cameras and optical sensors, then the plasma detectors and the less sensitive particle counters. Some of these instruments had been operating since the encounters with Jupiter and Saturn. Turning them off was like saying goodbye to old companions of the journey. But it was necessary. Every watt saved meant 1 more year of life for the radio transmitters. The engineers responsible for the mission now admit they are playing chess with death. Every maneuver must be calculated as if it were the last. In 2024, for example, another set of heaters, ones that kept critical circuits warm, was shut down. Many experts believed that the components would freeze and stop working, but surprisingly the Voyagers endured. Even enveloped in extreme cold, where the temperature nears absolute zero, they continue to transmit. It is as if the spacecraft have learned to endure the eternal winter of space. With each decision, the ground team makes a silent vow to keep the mission alive for as long as possible until the final beam of energy. And that final beam is approaching. Forecasts indicate that between the late 2020s and early 2030s, the nuclear generators will no longer produce enough power to sustain even the transmitters. When that happens, Earth's giant antennas will receive one last signal, one final sequence of data, and then silence. But the end will not really be the end, because even without power, the Voyagers will keep traveling. Their metal bodies, their antennas, and the Golden Record will remain intact for billions of years. With no atmosphere to corrode them and too few micrometeoroids to destroy them, they will become fossils of human knowledge, wandering through interstellar space. Voyager 1 will continue toward the constellation Ophiuchus. Voyager 2 will move toward the constellation Pavo. In about 40,000 years, each will pass just a few light years from other stars. These numbers are almost incomprehensible. 40,000 years is longer than all of recorded human history. When these probes approach their next stars, Earth may be completely different, perhaps transformed, perhaps unrecognizable, perhaps even silent, but there they will be, carrying with them proof that we once existed and looked at the sky with curiosity and courage. Meanwhile, here on Earth, the team that still cares for the Voyagers remains active, even with scarce resources. Many of the original engineers have retired, but their apprentices have taken their place. They are people who grew up hearing about the Voyagers and now bear the responsibility of guiding them to their final breath. They call it caring for the old ladies of space. The near future will be made of gradual shutdowns, fine adjustments, and small technical miracles. There will be days of silence, communication failures, and perhaps moments when all will seem lost until a new signal arrives, like a whisper from the abyss. That is how they have survived, at the edge of hope and physics, and when, at last, the final pulse of radio is transmitted, there will be no sadness, only gratitude, because these spacecraft, made of metal, wires, and energy, have accomplished what no other human artifact ever has. They crossed the solar system, touched the interstellar wind, and carried with them the portrait of Earth. Even when silent, they will remain the echo of our curiosity, a reminder to the universe that on a small blue point lived a species that sought to understand the infinite, and succeeded. As time moves forward and energy diminishes, the Voyagers face an even more subtle battle, not only against cold and distance, but against the physical wear of their own bodies. The greatest challenge now is no longer just the lack of power, but the maintenance of orientation. Keeping the high-gain antenna precisely pointed at Earth is what ensures that the signal, already incredibly weak, still reaches us. If the spacecraft turns even a few degrees off axis, the radio beam is lost to space and never returns. It is a delicate, almost impossible balance, sustained by a set of thrusters that should have gone silent decades ago. These attitude control thrusters, powered by hydrazine, are used to adjust the spacecraft's angle and ensure that the antenna remains aligned with ground stations. For decades, they acted as muscles of precision, but time spares not even the most meticulous engineering. The remaining fuel is scarce, and the valves after so many activations are degrading. Voyager 1, for example, has already gone through moments when its attitude control became unstable. It was then that the engineers did something unthinkable. They reactivated thrusters that had not been used since the early 1980s. The operation was nearly miraculous. With commands sent across billions of kilometers, the engineers managed to awaken the ancient thrusters, dormant for 37 years, and make them work again. When the confirmation signal finally reached Earth, more than 20 hours later, the team celebrated as if they had brought someone back to life. It was as if the spacecraft had remembered how to breathe. This technical feat, once deemed impossible, granted the Voyagers a few more years of stability and kept their antennas pointed toward our planet. But the deterioration continues. Each ignition burns fuel and weakens the ignition systems, and without fuel, the spacecraft will lose the ability to orient themselves. This means that even if their nuclear generators still provide power, the signal will eventually be lost in the void. Communication will end not because they have died, but because they will no longer be able to see us. Humanity will continue to call them, but the messages will echo into silence. Beyond the thruster problem, there is also the natural aging of electronics. The Voyager's circuits were designed in an era when chips were large and fragile. Decades of exposure to cosmic radiation have caused irreversible damage. High-energy particles from stellar explosions and the galactic background constantly strike the spacecraft, altering memory bits, burning components, and corrupting data. It was one of these invisible attacks that, a few years ago, nearly made Voyager 1 forget how to send information correctly. The engineers then had to perform a kind of digital surgery. They rewrote portions of the original code and relocated software functions to healthy sectors of memory. It was a painstaking task done blindly, with more than 40 hours of communication delay between command and response. Each line of code sent was a risk, but it worked. The spacecraft began to speak clearly again. It was as if a 90-year-old suddenly regained clarity for a few minutes to tell one last story. Cold is another constant enemy. As heaters are turned off to save energy, parts of the spacecraft operate at temperatures far below their original design limits. Metal cables stiffen, connections become fragile, and sensitive instruments begin to record electrical noise. Even so, the systems continue responding, stubbornly. It is as if each probe had developed its own resilience, a kind of survival instinct. Some sensors now operate far below their rated temperatures, and yet they keep working. The engineers joke that the Voyagers refuse to die, but perhaps the deepest threat is not technical, it is temporal. Each shutdown is a farewell. Turning off an instrument is not just a technical decision, it is an emotional loss. Each graph that stops being drawn represents a window that closes forever. The team knows that one day, perhaps soon, it will receive the last signal, a faint pulse of radio, an electric goodbye crossing the void for more than 20 billion kilometers, and then silence. Even so, the mission goes on. There is an almost spiritual serenity in the way the engineers face their work. They know they are keeping alive one of the last voices of the 20th century. They work patiently, aware that any day could be the last. There is something profoundly human in this persistence, continuing to care for something that has long outlived its expected lifespan. The Voyagers are now more than probes. They are witnesses of time. They carry scars, faults, and patches, yet they keep speaking to us. And as long as there is a signal, no matter how faint, humanity will keep listening. Because within each bit of data lies the memory of who we are, a species that refuses to accept the end. Even after crossing the edge of the sun's domain and entering interstellar space, the Voyagers are still working. What was once a mission of planetary exploration became a mission of cosmic monitoring. They no longer take pictures. Their cameras were shut down decades ago, but they still listen to the universe. They continue measuring the invisible pulse of the space between the stars, the interstellar wind, the galactic magnetic fields, the high-energy particles, and the distant echo of the sun fading in the background. The main task of the probes today is to study the local interstellar environment, a region that had never been directly measured before. Their still active instruments record the density and temperature of plasma, the ionized gas that fills the galaxy. These data are valuable because they show how the solar wind interacts with the interstellar medium, revealing how the sun breathes in the universe. Even billions of kilometers away, it still sends out particles that collide with the winds from other stars, creating a turbulent living boundary. The Voyagers also continue detecting the cosmic rays, energetic particles traveling at speeds close to that of light. These particles come from supernova explosions, from black holes, and from violent regions of space. Inside the heliosphere, the sun partially blocks them, but beyond it, where the probes are now, they arrive in far greater quantity. By measuring them, the Voyagers help scientists understand how interstellar space affects the radiation that eventually reaches Earth and future human spacecraft. Another instrument still functioning is the power magnetometer, which measures the direction and intensity of the magnetic fields around the spacecraft. These fields are the invisible skeleton of the galaxy, and studying them helps us understand how matter organizes itself on cosmic scales. Thanks to the Voyagers, it was discovered that the magnetic field of interstellar space is denser and more irregular than previously imagined. Instead of a calm vacuum, the universe between the stars is an ocean of trembling, pulsating energy. From time to time, the probes also detect the sound of interstellar plasma, electrical vibrations moving through the gas that fills space. When those signals are shifted into audible frequencies, they resemble a distant metallic tone, a humming voice of the cosmos. In 2021, for example, Voyager 1 detected a continuous hum coming from that plasma, a stable and persistent signal that revealed that the space between the stars is not completely silent, but filled with waves and pulses of energy. These data are transmitted back to Earth in incredibly faint signals, radio transmissions weaker than a household light bulb. And still, the giant antennas of the Deep Space Network, spread across the deserts of Australia, Spain, and California, can detect them. With each new pulse received, scientists extract fragments of information about a region of the cosmos that no other probe has ever reached. The irony is that even while studying interstellar space, the Voyagers remain deeply tied to the sun. It is the sun that keeps them oriented, the sun that once provided the energy that launched them, and the sun that defines the environment they are now exploring. They are in a way both outside and inside, free and yet still connected, as if they were distant daughters, still sending letters home while they drift toward the unknown. Today, the Voyager's measurements are the only direct observations we have from beyond the heliosphere. Everything else comes from models and inference. That's why every bit of information that reaches Earth is treated like scientific gold. The still active team analyzes every oscillation, every variation, every anomaly. The goal is to understand how the sun interacts with the galaxy and how interstellar space influences the cosmic weather that surrounds all star systems. While most space missions last months or years, the Voyagers have kept working for nearly half a century. And even though their instruments are now few, they still speak with the faintest, most distant voice humanity has ever heard. In a certain sense, What they measure today is not only the space between stars, but silence itself, the space between what we know and what we do not yet understand. There will come a day when Earth's antennas will turn toward the sky and hear nothing. No pulse, no echo, no signal. The last whisper from the Voyagers will cross the void and fade into the background noise of the galaxy. It will be the end of transmission, the end of telemetry, the end of contact. And yet, it will not be the end of the spacecraft, for even without a voice, they will keep traveling. They will keep moving forward, silent through the dark. The Voyagers no longer need Earth to exist. They already belong to the cosmos. When the transmitters finally go quiet, both probes will continue their outward journeys, moving at tens of thousands of kilometers per hour. Voyager 1 will keep its course toward the constellation Ophiuchus, while Voyager 2 will drift toward the constellation Pavo. They will both pass through regions no human being has ever seen, plunging into oceans of darkness where the sun is nothing more than an ordinary star. And for thousands upon thousands of years they will go on, two lost sparks carrying within them the story of a planet. In about 30,000 years, the Voyagers will begin to cross the Oort cloud, the invisible boundary of the solar system. This immense shell of ice and rock is both the graveyard and the cradle of comets, a gravitational frontier where the sun's reign ends and true interstellar space begins. The passage through this region will take 20,000 years. During that time, the spacecraft will drift among fragments of frozen worlds, silent spheres that have circled in darkness for billions of years. The sunlight, already weak and distant, will take days to reach them. None of their panels will reflect any shine. No shadow will be cast. Only motion, slow, constant, endless, and toward nothing. Even while crossing that vastness, the Voyagers will remain intact. Built of aluminum, titanium, and gold, protected from time by the vacuum itself, they will not rust, decay, or corrode. The absence of atmosphere is their shield. Each component will endure, preserved like a metallic fossil. If no collision strikes them, they may survive for pike of billions of years, long after the sun is gone, long after Earth has ceased to exist. When our planet is swallowed by the swelling of the dying star, when oceans evaporate and mountains dissolve, the Voyagers will still be there, traveling among the stars, carrying the golden record, the voice of humanity. Think about it. 20,000 years from now, entire civilizations may have vanished, languages may have been forgotten, continents may have changed shape, and still, the Voyagers will keep flying, silent, intact, carrying the sounds of rain, of wind, of birds, of laughter, the human heartbeat etched in golden copper, echoing through infinity. At that geological timescale, even the concept of now loses its meaning. What are 20,000 years against eternity? The Voyagers do not travel only through space, they travel through time. They are messengers from the past, flying toward a future that may have no one left to receive them. And yet, that journey is the greatest act of hope our species has ever made. When they finally escape the sun's gravitational reach, they will become artificial rocks drifting among the stars. Two human-made particles orbiting the galaxy like intelligent dust. They will be silent witnesses of a civilization that once dared to dream beyond its own sky. No other human artifact will last as long. No other symbol will carry such meaning. Each one carries the portrait of our home and the memory of our existence, and even if no one ever finds them, their mere existence is testimony enough. It is proof that human consciousness, at some point in time, chose to touch the infinite, that amid chaos, we decided to leave a sign, a trace, a signature. Thus, after the silence, the journey will go on. The Voyagers will keep moving forward, crossing geological ages, dancing among stars that have yet to be born, carrying with them the final whisper of Earth. And perhaps, somewhere in the future, someone or something will find them. Perhaps it will hear the sound of our rain. Perhaps it will recognize the laughter of a child. Perhaps it will understand that once, on a small blue planet, there was life, and that life wanted to be remembered. There is something profoundly symbolic about looking at the sky and knowing that somewhere far away, two small human-made machines are traveling among the stars. They are not just probes, they are mirrors of our own existence. The Voyagers represent everything that is most fragile and, at the same time, most magnificent about us. They are proof that a tiny civilization, confined to a pale blue dot lost in space, was capable of creating something that escaped its own world. And that in itself is a form of eternity. The human species is vulnerable. We live within a thin layer of atmosphere, dependent on a delicate and unstable climate, and our societies balance precariously between wars, crises, inequality, and budget cuts. Yet, we were able to build spacecraft that left the sun behind. The Voyagers were born in a time when the world was divided by ideologies and nuclear fear, but science managed to raise its head above politics and launch something greater than any border. And somehow, that gesture still echoes. At the height of our fragility, we chose to send hope. Today, the Voyagers survive not only against the forces of the cosmos, but also against the bureaucracies of Earth. Their budgets are reviewed annually. Their monitoring systems have almost been shut down multiple times, and every dollar allocated to their maintenance must be defended with arguments, spreadsheets, and meetings. It is a cosmic irony. The farthest human messengers from Earth depend on human goodwill to keep existing, and yet, every year the team fights and wins once more, extending the signal as one would protect a candle from the wind. In a world where news of wars and collapses dominate the days, remembering that there are 2 human spacecraft traveling through the void is an act of comfort. It reminds us that, even surrounded by chaos, we can still create something pure, something that seeks neither profit nor power but knowledge. The Voyagers are at the antithesis of destruction. While we build weapons and walls, they continue to build invisible bridges between stars. They teach us that humanity's true legacy does not lie in the borders we draw, but in our ability to look beyond them. And if one day we disappear, if our cities are swallowed by time, if our names are forgotten, the Voyagers will still be out there, silent witnesses that we once existed, that we loved, that we thought about the universe, that we left a message saying, "We are alive." Perhaps in a distant future, when another form of life finds these spacecraft, it will not understand our words, our music, or the images etched onto the golden records, but perhaps it will understand the intention. Perhaps it will sense that, by launching these probes, we tried to connect. We tried to tell the universe that life, however small, had blossomed here, and that for a brief moment, that life looked toward the stars and longed to touch them. The Voyager is more than a scientific achievement. It is a technological prayer, a reminder that knowledge can be sacred, and curiosity, a form of faith. When we look at the sky and think of the Voyagers, we are gazing at what is purest within us, the will to go beyond, even knowing there may never be a return. Ultimately, they mean that humanity is capable of transcendence, that we can build something that resists death, time, and oblivion. As long as a Voyager keeps traveling, there will remain an unbreakable line connecting the human heart to infinity. Before the Voyagers, the solar system was an incomplete map, a collection of points of light barely revealing their secrets. The best images of Jupiter, Saturn, Uranus, and Neptune were blurry spots captured by ground-based telescopes, and almost everything we knew about them was speculation. Only when the Voyagers crossed the depths of space did the unknown gain form, color, and texture. They transformed mystery into reality, and reality into wonder. Modern planetary science was born from what they saw. Without the Voyagers, we might still imagine moons as cold, dead worlds, but through them we discovered that Io is a volcanic world in constant eruption, spewing sulfur hundreds of kilometers high, the most geologically active body in the solar system. They showed us Europa, covered in fractured ice, hiding beneath its surface a liquid ocean that could harbor life. They revealed Ganymede, with its own magnetic field, and Callisto, scarred by impacts that tell the story of the solar system's earliest days. They changed our vision of Saturn, revealing that its rings are not a single structure, but a complex, living system shaped by tiny shepherd moons. They unveiled the dense, mysterious atmosphere of Titan, rich in organic molecules, a chemical mirror of Earth's primordial past. From these observations came a new era of research into the origins of life and the habitability of worlds beyond our own. And then came the ice giants. For the first and only time, humanity saw Uranus and Neptune up close. The Voyagers revealed supersonic winds, colossal storms, and nearly invisible ring systems, showing that even the most distant worlds are dynamic and alive. The images of Roma Triton, Neptune's moon, were a revelation. Geysers of frozen nitrogen erupting from a pink and blue surface. Signs of a world with internal energy, even billions of kilometers from the sun. These discoveries didn't merely fill gaps, they reinvented planetary science. Before the Voyagers, we didn't know that moons could have subsurface oceans, that planets could generate internal heat without sunlight, or that planetary rings could be natural laboratories for orbital physics. Every theory of planetary formation, atmospheric composition, and extraterrestrial geology was redrawn in the light of their data. The scientific impact of the Voyagers extends to this day. Later missions, Galileo, Cassini, Juno, and New Horizons, are direct heirs to their discoveries. Each one exists because the Voyagers opened the path, proved it was possible, and showed where to look. They set the standard, drew the route, and taught an entire generation of scientists to dream of the impossible. The data gathered by the Voyagers continues to be studied, even decades after their last planetary encounter. Many of these archives still reveal new details about atmospheres, magnetic fields, and chemical compositions. In some cases, modern models are compared with Voyager data to understand how planets have evolved over time. It is as if the probes were still teaching, even after half a century of travel. Without the Voyagers, we wouldn't know that the solar system is a living organism, dynamic, energetic, and constantly changing. They showed us that the cosmos is not static, but pulsating, that there are volcanoes where we thought there was ice, that there are oceans beneath frozen crusts, that there are storms billions of kilometers away still echoing within the sun's magnetic field. The Voyagers didn't just change what we know, they changed where it turned to how we think. They taught us to face the unknown with humility and method. They proved that the universe is more creative than any human imagination, and that behind every point of light, there is a world waiting to be discovered. The solar system was never the same after the Voyagers, and because of them, neither were we. The Voyagers proved that human curiosity can cross unimaginable boundaries, but now as they drift farther away and their signals weaken, a new question arises. What will come after them? If the Voyagers were the first interstellar messengers, who will inherit their mission? Who will continue the work of measuring the space between the stars and carrying humanity's beacon beyond the sun's protective bubble? In recent years, scientists and engineers have discussed creating a new generation of probes dedicated to interstellar exploration. The goal is not merely to repeat what the Voyagers accomplished, but to surpass it, to build spacecraft designed to cross the heliopause as their main objective, not as a byproduct of planetary exploration. These future messengers would be equipped with more efficient propulsion, autonomous navigation systems, and instruments capable of detecting particles, magnetic fields, and plasma waves with much greater precision. One of the most discussed concepts in the scientific community is the Interstellar probe, a mission proposal that has been under study by research centers for years. The idea is to launch a spacecraft capable of reaching interstellar space in just 15 years, something that took the Voyagers more than 30. This new mission would be the next logical step in the lineage of cosmic exploration, mapping the environment beyond the heliosphere, understanding how the sun interacts with the galaxy, and observing for the first time systematically the space between the stars. But as always, scientific progress runs up against human reality. Just as it happened with the Voyagers, the fate of these future missions depends on budgets and political priorities. Within space agencies, there are constant debates about where to invest. In Mars exploration, in the icy moons, in space telescopes, or in probes that will travel so far that they might never yield immediate results. It is a dilemma between the present and the eternal. And once again, it is up to humanity to decide whether to keep looking toward infinity or to let the horizon close. It is strange to think that while the Voyagers travel through interstellar space, fighting to remain alive, their continued operation on Earth must be defended through meetings and reports. Some question the cost of maintaining communication with two such distant spacecraft, but others understand that beyond science they are heritage of humanity. To defend the Voyagers is to defend our capacity to dream, and to plan their successors is to ensure that this dream does not fade with the final signal. These future interstellar probes, when launched, will carry the legacy of the Voyagers. They will bear decades of knowledge, technology, and scientific poetry. Perhaps they will also carry new messages, new records filled with voices and music from Earth, updated with the culture and understanding of the 21st century. They will be new bottles cast into the cosmic ocean, drifting toward destinations no one will ever see. The idea of maintaining a permanent beacon beyond the heliosphere is seen by many scientists as a civilizational duty. Just as we maintain observatories to look at the sky and telescopes to glimpse the universe's past, we must also keep messengers out there, probes that, from beyond the solar bubble, tell us how our home interacts with the galaxy. It is a way to ensure that humanity remains present, even in silence at the edge of infinity. The Voyagers were the first step, but the journey is far from over. Interstellar space is vast, and every measurement taken by a probe is like a grain of sand before an ocean. Still, we go on, because the drive to explore is etched within us. And as long as there are engineers willing to dream and scientists determined to persist, there will always be a spacecraft ready to depart. Perhaps one day, long after the Voyagers fall silent, a new probe will cross the same space and detect a faint signal, the distant echo of its ancestors. Perhaps it will recognize their presence, as one might find an ancient footprint in the desert. And in that moment, the story will come full circle. The cycle will begin again. The future messengers of the sun have not yet been born, but they are already inevitable, because human curiosity is stronger than oblivion. And as long as the will to understand the universe exists, there will always be a spacecraft being built, always something ready to move forward. Now, imagine the silence. A silence so deep that no human word has ever filled it. Out there, sunlight no longer reaches. Darkness is absolute, and the cold is so complete that time itself seems to have stopped. In that vast stillness, two small spacecraft continue to drift, invisible even to the stars. They move forward without destination, without return, carrying within them one single thing, a message etched in gold, written with sounds, images, and the hopes of a civilization that wished to be remembered. The Voyagers are alone, traveling through an ocean where there is no wind, no north, no echo, and yet they continue. Inside each of them, the golden record spins silently, holding human voices saying hello in 55 languages, holding music that speaks of love, of sorrow, and of joy, holding the sound of the wind blowing through Earth's forests, of rain falling upon the soil, of a child's laughter. All of that now floats in the void, fragments of a world that millions of years from now might no longer exist. Perhaps no one will ever hear that message. Perhaps it will drift forever, lost among dead stars and receding galaxies. And yet, it exists. It is out there, like a candle burning in the dark, a sign that at some point in the history of the cosmos, there was consciousness. There was life that wished to communicate. There were beings who looked into infinity and decided to leave a message, even without knowing if anyone would ever hear it. And maybe that is the true meaning of the Voyager's journey, not the destination, but the gesture. The decision to cast a bottle into the cosmic ocean and accept that we may never know if anyone will ever find it. Because what matters is not the answer, it's the message. It's the act of saying, we are here. When we think about it, human existence itself seems to gain new meaning. Everything we do, our discoveries, our loves, our art, are in some way attempts to send messages to the future, attempts to resist oblivion. The Voyagers simply carried that impulse to the extreme. They turned curiosity into motion, science into poetry, and technology into immortality. There is something profoundly human in imagining those probes crossing the darkness. It is like thinking of two lonely travelers, eternally faithful to their mission. While Earth changes, ages, and transforms, they continue. They cross clouds of interstellar dust, pass by stars that are born and die, and move onward, not knowing where they are going. They are in no hurry, because eternity has no clock. And so, with every galactic rotation, the Voyagers carry with them a question that may never be answered. Who is listening to our message? Perhaps no one. Perhaps everyone. Perhaps the entire universe. But deep down, the recipient has always been ourselves, because in sending them, we learned that we don't need to be eternal to leave something eternal behind. The Voyagers are a reminder that life is rare, precious, and brief, and precisely for that reason it has value. They are proof that consciousness can cross time, and that human curiosity is, in itself, a form of light. So next time you look at the sky, remember, there are two small spacecraft traveling for you. They carry the sound of your planet, the music of your species, the echo of your very existence. And even if they never find anyone, they will keep telling the universe with serenity and courage, "We were here." If you've made it this far, tell me where you're listening from right now. Leave your like, comment, and share this video with someone who also finds wonder in the universe. Subscribe to the channel so we can continue exploring the stories, mysteries, and discoveries of science together. Because as long as there are questions, we will keep searching for answers. Sweet dreams, and see you in the next video.